Hello and welcome to my presentation on self-learning optical music recognition, how I'm teaching the machines to read music scores. My name is Alexander Pacha, and this video is a re-recording of the dissertation defense that I gave on the 4th of July 2019 at the Technical University Vienna. Let's start with the question, what is optical music recognition? You start off with music scores, you take a picture of these, you feed that image into an optical music recognition system, and the system processes and recognizes the scores and produces a machine-readable version of that music score. That's basically the idea of optical music recognition, and when I started my dissertation, I had some time to do some research on various definitions, and I figured out that there is not a unified definition of what optical music recognition actually is. I mean, this is a good intuitive understanding of going from an image of music scores to a machine-readable music score, but upon collecting various definitions, I figured out that there is a wide range of various definitions. So we collected over 130 different definitions and created this graph. And so you can read from the left to right, and probably one of those definitions already exists. For example, OMR is the task of automatically recognizing handwritten music scores into a MIDI file. Now you will notice that there are a lot of different things here. So we tried to put an umbrella over all of these definitions here because some of the definitions are too narrow. For example, having just printed music into a MIDI file. Why not producing other things? That's not a kind of definition that is broad enough. On the other hand, some definitions were too vague. One prominent example is describing optical music recognition as OCR for music. So we tried to come up with a better definition, and here is how it goes. So optical music recognition is a field of research that investigates how to computationally read music notation in documents. Now let's break that down a little bit. Why field of research? Well, obviously it's some research that is being done, and all of the other things like a task or a program usually have a clear input and output, whereas optical music recognition has a variety of inputs and outputs. Computationally reading is the most concise way of producing, of actually reading something in documents. If you say just transcribing or digitizing, that would probably indicate something else. So for example, if you take an image with a digital camera, you already digitize music scores, but that's not the point in optical music recognition. You actually want to read the music scores. And music notation documents, because we're interested in music that is being written down with music notation and embodied in documents. So this is the full definition once more. Optical music recognition is a field of research that investigates how to computationally read music notation in documents. And this is one of the major contributions in the paper Understanding Optical Music Recognition, which is currently under review for the ACM Computing Survey. And it has been authored by my colleagues Jorge Calvo-Zaragoza, Jan Hajic, and me. And when I refer to we, I usually refer to this group of three people, because we authored many papers together, and we always paid close attention that we contributed equally to our works. So that's optical music recognition. What can you do with it? There is, again, a wide variety of things you can do. For example, you can listen to songs you cannot play. You can educate musicians to learn from examples by just listening to them. If you say play the flute, but you don't have someone accompanying you right away, why not just scan the piano voice, let the computer play the piano voice, and you can practice the flute to play along. You can create an auditory version of handwritten drafts, which is particularly important for composers, because even nowadays, many composers still write, with pen, paper, their compositions. And if you want to listen to it, well, then you have to digitize it or play it on a piano, for example. Also for musicologists, there are a number of applications. For example, you can preserve ancient manuscripts and make them accessible and searchable. And all of a sudden, if you digitize and process thousands of scores, you can start doing musicological analysis at scale. You can also re-edit and create derivatives of music, which is similar to sampling in the audio domain, where you take a snippet of, say, a famous or a widely known song, and you mix it and create something new. And last but not least, you can convert scores to different formats. Say you've got mensural notation, scores in mensural notation, and you want to convert them into modern notation for people to being able to read it better. Optical music recognition touches a lot of subjects, and most prominently, it's part of computer vision and vision science. Of course, there's also an overlap with music information retrieval because of the domain. And as a user, practicing musicians and composers obviously have an interest in optical music recognition, as do have people from digital libraries and musicologists. And for me, it was particularly useful to both have a strong background in computer science and computer vision, as well as music. So I'm a musician myself, so it really helped to appreciate the complexity and the challenges that both parts of this research area, present to one. To understand optical music recognition the best way, it's probably best to start with how music is being created. Music is basically an idea initially. So you have a composer, and he or she envisions a certain melody, a rhythm, and sound, and they try to capture this idea. And one way to capture this idea is by conceptualizing it with notes. Notes have the basic properties of having a pitch. So how high should it be? When should it start? The onset. How long should it take? The duration. How loud should it be? The velocity. And which color of tone should it have? The timbre. And there are a bunch of conceptualizations, but once you have the conceptualization with notes, you can basically write it down. But even then, there are many decisions that you have to take in to ensure that whatever you're writing down can be understood by other musicians. And that process and these design decisions that you're taking, we call engraving. And music notation is one way to engrave notes. And for example, you can think of 4 different voices, splitting them up or putting all of them in the same stave. One of these options will be better readable, the other one probably not as good. And last but not least, you actually have to embody it into a physical document. That can be writing it down on a piece of paper, or it can be a PDF document or something on a computer. But eventually you have to produce an actual document. Optical music recognition then takes that document and inverts the process. So you can go back and try to recover the music notation, how the music was written down, or you can go back 2 steps and try to recover the music, which is actually captured with music notation. Keep in mind that going back through this process 1 step only to the music notation can in fact be harder than going back 2 steps. Why is that the case? Because music notation is much more complex and much richer in terms of what it can express than just the notes with pitch and duration. So if you just want to recover the music semantics, you're usually interested in replayability. For example, you want to listen to a piece of music. If you also want to play it or read it as a human, you usually refer to this as reprintability, because then you also want to know how was the music written down, how was it laid out, because that is what makes it understandable to humans. Optical music recognition has and still is frequently underestimated. And one reason is that people see an example like this and they think, especially when you know a good thing about computer vision, then you see, okay, there are straight lines, and many people know how there are like good algorithms for finding lines. So let's use a line detector to find these 5 structural elements here. You can remove them. Then you can apply another line detector to detect the vertical lines, and then erosion to find the blobs, and so on and so forth. So they think, okay, well, from a visual perspective, that's not too hard. But truth is that you more often encounter scores that look like this. So the lines are not perfectly straight. There is some deformations, noise, and so on and so forth. So it can be much harder to do all of these things. And many students that start, they kind of go and try to detect the stuff lines with easy algorithms like projections, and they stumble across real life scores, and then these things fail. And when you take it one step further, it even gets more difficult, especially when you start dealing with handwritings. This is an example from the CVC Muskema dataset. And I don't even want to start with Beethoven's handwriting on the left, because that's super hard even for humans to read. Luckily enough, there are some people who are able to read this. Otherwise, we would have lost this great music of Beethoven. On the right-hand side, you see orchestral scores that exhibit a unique property of music scores, namely that you have very densely packed information. So there are, I guess, more than 1,000 objects in just that little page on the right, like 1,000 primitives, dots and lines. And you have to recognize all of them to correctly recover the music here. But this graphical complexity of having dense scores and having all sorts of artifacts that might arise from the image capturing process. You also have overlapping symbols, but that's only the graphical complexity. Optical music recognition has an entire another dimension of complexity, which is inherent to music notation, this structural complexity, because it is a configurational writing system, which means that not the presence of a certain symbol determines the meaning here, but the context. So if you have a note head, it doesn't mean anything by itself unless it is put on one of these 5 lines or in between one of these 5 lines. It receives a reference by a clef and so on and so forth. And there are many of these rules where you can put stuff and what it means. And these syntactic and semantic rules are unfortunately often violated. Or there are ambiguities. For example, when you take a look at this area that are highlighted here with the red box, a small dot that is next to a note head can mean 2 things. It can increase the duration, would be then an augmentation dot, or it is a staccato dot, which reduces the length of the played note a little bit. And in this case, we have both. So it's below one note head and right to another note head. And for the computer, this can be really challenging. How humans usually deal with problems like these is that they come up with hypotheses, and one of the hypotheses here is completely nonsense. Therefore, we rule it out and we go with the other one, with the duration dot here. There is a second example here, which clearly shows the violation of musical semantic rules. So in a measure, you usually have a certain number of notes. That's like the timing. But in this example, if you actually count the number of notes, you will realize there is 1/16 too much in this measure. So, and that's not some modern composition where someone was experimenting. This is by Frédéric Chopin, like a really famous composer who was frequently violating the rules of music notation. So I think this actually brings us to the natural limit of OMR. So at the point where musicians start to disagree about how it's being played and interpreted, this is definitely the end of OMR, where it can't go beyond. And when you consider all of these syntactic and semantic rules and think about building a system that is rule-based, it's a very, very hard challenge, and I would say nearly impossible, because you would have to implement so many exceptions that eventually it will blow up the system. So, is all OMR impossible? Is it too hard to even try? No, of course not. Because depending on what you want to achieve with optical music recognition and how much information you want to extract, you can already do that pretty well. And we came up with 4 categories for understanding or categorizing the outputs based on the level of comprehension, how much information you need to understand in the scores. The first category would be document metadata extraction, where you just want to get some information about the score. Search is clearly to be able to search within music score. Replayability wants to create an audible version of music score. And only for recovering the music notation fully, which we call structured encoding, you need to comprehend all of the information that is written down in music notation. To make this a little clearer, I have a nice example how you can visualize or think of these 4 categories. So here's a screenshot of a Wikipedia page, and if you just want to ask whether this screenshot contains an image or not, that would be metadata extraction. And the answer is yes. On the left top, there is the logo of Wikipedia. When we go into search, you can ask something like, where is the word muse? Or does it exist in the text that is written in this article? When you go even one step further, replayability would be similar to reading out loud this article. Then therefore you already have to take care of the reading order and making sure that the system actually knows how to, process different blocks of text. And for recovering the structured encoding, that could be compared to asking, please give me the HTML source code for that website. And as you can imagine, there is not one truth, one universal truth of that source code. I mean, there can be various ways to achieve the same visual result. And that's about the difficulty of optical music recognition. So if people say, oh, that's not too hard, well, you can give them this example and ask them whether they think it's hard or not. Traditionally, it was approached with the following pipeline, which was, I think, originally proposed by Bainbridge and Tim Bell in around 2000, and then refined a couple of times, but it more or less stayed the same. That's the version of Anna Rebello from 2012. And I'm not going to go into all of the details, but basically you have 4 major blocks. One would be to do some pre-processing. A second would be to find the objects, with usually stuff line detection and removal being very prominent in those in that part. And there are 2 more steps where they try to recover the music notation and finally construct the output representation. For my dissertation, I took that pipeline, I slightly reformulated it into the following 4 things to enable self-learning most of the steps that are part of this. So the first step of my pipeline would be to analyze the structure, to find the staves, find measures, and kind of do this pre-processing. The second step is finding all music objects. The third step would be recovering the relationships between the detected objects. And last but not least, you have to create an output, that desired output that you want to have in that you want. For example, it can be an MEI file or a MIDI file or music XML that you can further process down the road. And during my doctoral research, I mainly worked on the first 3 steps of this pipeline and not so much on the fourth. And I will tell you why later on this talk. So let's start with structure analysis, the first step. And the easiest question you can ask at the beginning is, well, does this image contain music or not? So to classify an image, whether it contains music or not. And I published this in my first paper, which was called Towards Self-Learning Optical Music Recognition. And for that, I collected a large data set of over 5,000 images. 2,000 of them were image scores, and the rest were natural images of, dogs, cats, but also documents that look much more like music scores. And the task for the machine was to learn how basically scores look like. And if you know deep convolutional neural networks, and if you're aware of deep learning, then you will probably know that this is a kind of easy challenge. Therefore, it will come to no surprise that I achieved 100% accuracy on this data set. And at first I thought, okay, well, that's really too simple. Then I figured out there are some confusions with tables that, look similar, but it was easy enough because I just added more samples of tables into the category of other things to just provide more negative examples. And then the network was able to kind of do this really well. So I thought it was too simple and probably no one's going to use it. But I was very happy when a librarian approached me and she said, well, they've got a real world use case for this, because in their library, they're processing a lot of documents that come in every day, and they would like to know whether the images and the documents they get in their inbox contain music or not. So there is some real life use case already for this, which made me really happy. Moving on to one of the most recent works that I've been doing, which is still basic kind of structure detection, which was on detecting and aligning measures across music scores. I did this together with Simon Waluszek and Aristoteles Hadjiakos from Germany. And this paper is about to be published at this year's ISMIR conference. And the idea is the following. So imagine you're a musicologist and you're working on a critical edition of one piece of music. You've got 5 different editions that were copied and edited by different people, and you want to compare these 5 versions and look out for errors, for differences, for omissions, for edits. So it would really be useful to kind of quickly find those differences. And that's the idea of this paper, of our work here. So what we did was we manually annotated over 16,000 pages of music, including manuscripts as well as typeset scores. And we annotated them measure by measure, meaning that all instruments that play at the same time, that's kind of a measure, and trained a neural network to find those measures, to find the bounding boxes of all measures automatically in music scores. Then there was a second network which compared those detection results to each other and tried to identify whether or not 2 boxes contain the same content, musical content or not. That was being trained by using a triplet loss function and again a deep convolutional neural network. The idea with the triplet loss is that you have one reference image, and then you've got one positive example which contains the same, and one negative example. And the effect is that the neural network learns an embedding where measures that contain the same content will be placed closely in that space. And the last step was to use dynamic time warping to align the sequence of measures with each other. And on the right, you can see the user interface of the system. This big black blob, I could say, is a matrix where each row and column corresponds to one measure. And the blue diagonal line is the correspondence. Ideally, you will have a one-to-one correspondence between the measures of different editions. But if something goes off and there are, say, measures are missing or there's a repetition of something, then you'll get a vertical or a horizontal line in this graph. And then you can just click on it, and on the right-hand side, you will be presented the excerpts that you actually can take a look at and investigate further. Music object detection is the second big step of the pipeline that I was working on. And I started with an easier task, not doing the full detection immediately, but first starting with classification. So I wanted to see how well can a machine learn to do this classification, especially with deep learning. And the answer is really good. So I published this in an article called Towards a Universal Music Symbol Classifier. And I collected a really large set of isolated symbols with more than 90,000 symbols from various datasets, both typeset and as well as handwritten symbols. There were some issues here because some classes were much more prominent and more dominant than other classes. So you had to take care of balancing that out during training to not mess up with your classifier. But turns out that a convolutional neural network can easily learn to classify isolated symbols. It was fairly simple to handle both handwritten and typeset symbols, and I got over 98% accuracy, which is interestingly similar to the human performance. So I also gave the same task to humans and asked them to classify it, and the machine actually outperformed them slightly because some symbols were ambiguous, and when the symbols were ambiguous, you had to make an educated guess, and the convolutional neural network simply had more experience with that data set. On the right hand side, you can see the network architecture, but I'm not going to go into the details because it's a fairly straightforward VGG-like convolutional neural network. And all of the hyperparameter combinations that I evaluated worked very well. This network worked a little bit better than the others, but all of them were, say, in the range between 95 and 98% accuracy. So, if classifying symbols works so well, let's go and detect the symbols. That's, the logical next step. I did this work together with Kwon Choi and other researchers from France, and published our work in Handwritten Music Object Detection, Open Issues and Baseline Results at the workshop on Document Analysis Systems in Vienna in 2018. So the main idea was, please give me all the things that are in the music score. And to do so, we used 140 handwritten manuscripts from the Muskema++ dataset, and we cropped the images. First, given that we had annotations and ground truth, we knew where the staves were, so we cut the images by stave, and then further cut them vertically to have kind of only small snippets. And we evaluated various modern deep learning object detectors, including single shot detector, RFCN, and faster RCNN. And the results were really good. So we got over 80% mean average precision on the test set and over 94% weighted mean average precision on the test set. The discrepancy here is naturally because some classes were much more prominent than others, and those well-detected classes, those more common classes were also better detected than the rare classes. Therefore, the weighted mean average precision is slightly higher. One very interesting insight we got here was that removing the stuff lines did not help us. Like, the results were exactly the same whether we had stuff lines in the image or not, which is a really strong sign towards that you basically don't need stuff line detection and removal anymore. I mean, you can still do it, but it doesn't help. Ideally, it doesn't hurt as well. But usually when you do a pre-processing step and you modify the image, there is always a risk of introducing artifacts. Therefore, deep convolutional neural networks can basically ignore or learn to cope with stuff lines, so you don't have to remove them anymore. Well, if it works for cropped images, let's go and detect symbols in the full score. Again, my colleagues Jan and Jorge and me tried to do exactly that, and we published our findings in the baseline for general music object detection with deep learning in the paper, in a journal article. And what we did was we compared 3 competing approaches with fast RCNN, the one you've just seen, RetinaNet and UNets. UNets the approach was proposed by Jan Hajic. And we took 3 different data sets and ran exactly the same training and detection and evaluation of these 3 detectors on those 3 data sets. And it turned out that they didn't perform too well. Damn. Well, that wasn't too good. So we sat back and thought, okay, why is it that these things not work too well? I mean, we had 80% on those crops. And then we realized a few things. So one was that we changed the metric. We changed to a more strict metric, namely to the COCO metric, which is today often used for object detection tasks, whereas the first one was just the Pascal VOC metric, which is more generous and generally gives better results. And the second thing was, especially for the fast RCNN and RetinaNet detectors, we had to downscale the images and reduce the image resolution to fit them into memory, which is just a technical limitation. I mean, there's no other reason why you would downscale the images. And that really hurt the performance. You know, the small dots and all of these tiny objects, when you downscale the image, you blur them and you introduce new artifacts, which of course make the detection much harder. So, is there an alternative? Well, there is an alternative between having the full page and the crops, which is to just crop them by stave and not chop them any further, because there are many objects that cross measure boundaries, or like that horizontally span a large range, but not so much vertically. So that's the final detector I was working on, which was used for the paper I will show you on the next slide. So again, same approaches for the crop images, but just cropping them stave-wise. And I think it looks really good. I mean, it detected almost all of the objects I can see here. Of course, like some things might have been misclassified, but in general, I would say that detection here worked very well. So if you got the detection results, what should you do next? And what I propose to do next is to kind of make sense out of these symbols and do the music notation assembly. We tried to recover the relationships and automatically build and learn how to construct a music notation graph. This paper is also about to be published at this year's ISMIR, and again with my colleagues Jorge and Jan. So what is this music notation graph that I'm referring to? Let me give you an introduction here. I mean, you can already see it here in the image, but basically you have a graph, and that graph holds music primitives that come from the detection. Those are the vertices of the graph, and the relationships between those primitives are the edges. We propose to have two different types of edges: the syntactic edges that refer to objects that belong together. For example, a note head and a stem can belong together. And there are precedence edges, which define the temporal order. And you might think, why do you need precedence edges? I mean, just read from left to right and you should be fine. But when you think back of the example I had previously from Chopin, if you do not introduce precedence edges, it might happen that this extra note that was in the music would have been played at the same time the note started on the other stave. And that, of course, would have been wrong. I mean, visually, we saw that. So therefore, it really can help to have these precedence edges. And what we did is we trained a neural network to do binary classification, basically asking, is there an edge between two primitives? And so how do you do that? You have three inputs: the image crop, which is just a snippet or a region of interest where the two objects are. Then a second channel is the mask of the first object. On the right hand side you see three examples. For example, the note head would be like this cyan object, and the mask of the second object would be the green one. That's the third input. And the three examples here on the right, you can see the first one on top is a positive example. So the note head and stem, they go together. The middle one is an easy negative. The slur and the note head do not belong together. And the last one is a tricky one, because we again have a similar piece that we saw before, where we have an augmentation dot that is underneath a note head. So that's a hard negative example. And the performance was good. We tried it on two different data sets. Well, it was the same data set, but on two different conditions. One was the perfect detection, the ground truth of what humans annotated. And then we also evaluated this notation graph learning on real, actual detection results, on the image, on the detection results of the image that I showed you before. So I'll just quickly go back, because here in this figure you can see it quite well. So the red edges here would be the syntactic edges, and the purple line which goes through the note heads would be the precedence edges. So that works really well. And the reason for constructing this music notation graph, as I've promised you, like why would you do this, is that if you have an intermediate representation that contains all of the necessary information, you can have someone else who might not be an expert in computer vision or in deep learning, who can take that graph and construct a particular output that they want. Say you want to play it back, you can write a converter from this notation graph to MIDI. And that, I think, would be the task or the duty of someone who is actually familiar with the target music notation format. And you also need to be aware of the music that you're actually trying to read, because depending on the time it was written, it can actually mean something different. And you always have to take that into account. Which brings us to a simplified OMR pipeline for Mensural notation. Mensural notation is kind of a predecessor of modern notation, and it's graphically monophonic. So there's just one voice per stave, and you can therefore just read it left to right. And in this work presented last year at Izmir by Jorge and me, we had scores that looked like this. And our proposed approach was to jump right into the thing and do the music object detection, find all of the symbols. The second thing is to classify the positions, to figure out at which vertical position they are. So basically something like relating to the pitch. And the third step would be to do the semantic reconstruction and then, for example, encode it into modern notation. The third part is actually under research by David Riso. So for that paper, we didn't include that part because it's still ongoing research. But he's building on top of what we did with the first two steps. So we had 60 high quality images that were manually annotated with over 15,000 symbols out of 32 different classes, which is less than the approximately 100 to 150 classes you have in modern notation. Again, we detected all of the symbols with a deep convolutional neural network and faster RCNN detector, similar to the object detectors that you saw before. The really cool new thing here was the position classification, which is inspired by the way how humans actually figure out the vertical position. They don't look to the very left and then they count the pixels to the middle to figure it out, which computers sometimes do. But just take a look at the surrounding area. So we crop out a sub-image, we subsample the image where we have a detected object, and trained another deep convolutional neural network to classify the vertical position. So the object that we wanted to classify was always placed in the center. And in case we reached the end of the page, say, well, that can easily happen, we mirror padded the image to make it look more realistic and not have big black regions all of a sudden in the image, which might confuse the network even more. And position classification worked exceptionally well. It worked so well that when investigating the error cases, we figured out that the errors the network made actually was the truth. They were human annotation errors. So the humans made an error and the network figured out those things were not right. And that was really cool to see. So one of the big questions is, how good is OMR now? I've got one last paper that I'm going to show you here, which was conducted again by Jan, Marta, Jorge, and me, and presented at the Digital Libraries for Musicology last year, and named how current optical music recognition systems are becoming useful for digital libraries. So we had a couple of questions that we thought, well, does it work? Is it useful, whatever we have so far, even though there are some errors and some mistakes that the OMR system does? And we tried to compare how two modern OMR approaches fare when they compete against each other. So one was the full pipeline with the UNet detector and connected components, and the other approach was an end-to-end approach where you directly feed in the music, like one stave, and it outputs the sequence of notes that are in that stave. And we had two questions initially, which was find all duplicates to do a page query. Imagine like you have a library with duplicates. Well then, please give me all the duplicates. And a snippet query was to find just a short segment, basically one stave, out of our entire data set. So the dataset we used for these experiments was the CVC Muskema CVC Muskema dataset, because it is a natural fit. It has 20 different songs transcribed by 50 different musicians. So you've got 50 duplicates of each song in the dataset. And how to evaluate this was that we asked, well, we used the metric, the mean average precision, which is a retrieval metric. And we imagine that you get a ranked list of results, and a human would stop when the first non-duplicate shows up. And if you just want to retrieve one duplicate, that would be the MAP at 1. If you want to get 10 duplicates, MAP 10, and 49 would be give me all duplicates. And we had two different conditions. One was OMR to OMR, and the other one was a cross-model condition. OMR to OMR we used for, so here both the dataset and the query were processed with the same OMR system, which has the benefit that if the system has certain limitations, they hopefully cancel out. Whereas in the cross-model setting, only the dataset was processed by the OMR system, and we used the ground truth as a query, which would be similar to a human who's, say, entering a melody on a MIDI keyword. So that worked really well, especially for the page queries. That's fairly easy because the sequence is very long and you can very well find duplicates. For snippets, you can immediately see that the performance decreased a little bit. So it was still fairly good, but not as good as the page queries. Next, we had a question of how similar things are. So if you take music and you kind of process it down to MIDI, and then we kind of apply a MIDI similarity metric from the melody shape library, then it would be interesting to see how well the OMR system worked. And we did this with the Primus dataset, which contains the incipits of the rhythm dataset, I think 1,600 kind of incipits, and computed the correlation coefficients, Spearman and Pearson, and they both show good trends that you can probably swap the ground truth with OMR systems for many cases because they show the same trends. And speaking of trends, we did one last part for that paper. We tried to reproduce a quantitative study by Vos and Trost from 1989, where they tried to characterize Western classical music based on the joint distribution of ascending and descending interval sizes and directions. So we did a statistical analysis on the Primus dataset as well. And on the left side, you can see the results from Vos and Trost. And on the right-hand side, you can see the results from the Primus dataset. And the interesting thing is that the green bars are the ground truth from MIDI, and the yellow bars are what the OMR output would be. And you can see that they're both similar. So if you had used OMR for the study back then in 1989, you would have received similar trends with OMR, which is cool, I would say. So wrapping up, there are some more contributions that I didn't go into detail so far. I collected a large overview of OMR datasets, which is a GitHub page and a GitHub repository that people can consult and learn more about datasets. I compiled with Jan and Jorge the probably largest bibliography on OMR, which is also available on GitHub, which also has the BibTeX files. So you can kind of just grab that one and use it for your own research and don't have to worry about, whether the authors are correct and so on. I organized a bunch of workshops, did a tutorial at last year's Izmir on optical music recognition, and I'm also maintaining some part of social media and our website, as well as the Muskema++ dataset right now. And I also created a tutorial video for Muskema++. So if you don't know it, feel free to go to YouTube and check it out. Summing up, optical music recognition is the research field that investigates how to computationally read music notation in documents. And it's still frequently underestimated, especially the semantic reconstruction step, because, music is really complex. It virtually knows no limits. Therefore, the music notation that is used to capture it also has to allow all of this complexity to be represented with it. I tried to approach optical music recognition with kind of mostly self-learning and deep learning. So I asked the machine to please learn the things by itself, given a certain amount of supervision. And it worked exceptionally well. So I was really surprised to see how well deep learning was able to, detect symbols and do other parts that really are essential to optical music recognition. There are some alternative approaches that I want to mention here. For example, this end-to-end approach where you just feed in one stave and get out the fully kind of encoded sequence. But those approaches and those systems are unfortunately still limited, for example, to monophonic music and so on. But it doesn't mean that in the future someone doesn't come up with a clever idea how you can actually handle complex pieces with an end-to-end approach as well. All of the resources and research and source code that I did is publicly available on GitHub. I published it under the most liberal license I could find, the MIT license, for other researchers to be able to pick it up and work with what I've done so far. I tried, to test my source code and document it as good as I could. And I truly believe that with what I've seen in the last few years, OMR systems, especially robust OMR systems, have definitely come within reach. And I'm sure that in the next few years, there will be some systems that will work really well for both handwritten and typeset music. So ideally, next time I'll arrange something for my choir or do have to digitize some old scores. I don't have to do it by hand by typing it in on a computer, but hopefully I can use a good and robust OMR system to do it for me.